All right, so we're going to talk about some periodic relationships among the elements. And this periodic, you may wonder, it's called the periodic chart or periodic table, comes from the fact that the properties of these elements are systematic. And a lot of this was figured out before we knew anything about the internal structure of the atoms, how the electrons were arranged, because they could arrange them just by physical properties at this point. So things like their melting point, boiling point. For example, a metal could be a shiny when you cut into it or gray when you cut into it. All of those properties they used to arrange the periodic table and got pretty close to what our modern periodic table is just with that data. Well, we know now that the periodic table, the underlying physics behind it are these electron configurations. And these two columns on the far left, this is the S block. These columns here on the far right in green are the P block. The light blue columns here in the middle are the D block, and the ones down there at the bottom are the F block. And that's the underlying physics that explains the related chemistry, is that they have similar valence shell electron configurations. Well, let's now talk a little bit more about something called effective nuclear charge, and that will dictate a lot of the other properties of the atoms. So we have, let's start pretty simple, lithium. It has 3 protons in the nucleus and it has a total of 3 electrons. The first 2 electrons are in the 1s orbital, which is really close to the nucleus, and then the third electron is in the 2s orbital, which is a bit further from the nucleus. Well, it ends up that this electron here shown in green in the 2s orbital, it doesn't feel the full 3+ charge from the nucleus because it has these negatively charged 1s electrons in between it and the nucleus most of the time. These 1s electrons do something called shielding. They're shielding the nucleus they're shielding the charge of the nucleus from this outer lying electron. And this is a general thing that happens. Inner electrons do a good job shielding for electrons that are further from the nucleus. Well, let's see how this effective nuclear charge changes as we move across a row on the periodic table. And let's start here with lithium. And here, this in green is the effective nuclear charge. As we go from lithium across to neon, the effective nuclear charge increases. And so the outermost electron of neon is much more tightly bound to the nucleus. It has a charge of 5.85 that it feels, versus the outermost electron in lithium, which is attracted to the nucleus only by a charge of 1.3. And so here's one of our first trends. Proceeding from left to right across a row in the periodic table leads to a steady increase in effective nuclear charge. Well, as we go left to right, it increases. So what happens when we hit the far right of the periodic table? And so let's start then with neon. That's the far right of the first full row of the periodic table. As we go neon to sodium, the effective nuclear charge now rapidly drops off. It goes down. So we were at neon. We go to sodium and it drops down. But then after we go sodium to magnesium, it starts to increase again. And so this is generally what happens. We start with a low effective nuclear charge on the left side of the periodic table. The effective nuclear charge steadily increases as we go from left to right. And then on the right is the maximum value of the effective nuclear charge. And we go back to the left and it drops down to a small value again. This happens because we increase the principal quantum number. In going from neon to sodium, we went from an n equals 2 orbital to an n equals 3, and what that causes is this big increase in shielding. So those electrons are shielded from a lot of that nuclear charge, and you'll see the effective nuclear charge value decreases because the shielding increases when we start a new principal quantum number. And this is because the electrons in the 2s and 2p do a good job shielding the electrons in the 3s orbital. All right, well, here's the trend again. So the highest effective nuclear charge is up in this upper right-hand corner, and as we go across any row, we start with a small value, and it increases as we go left to right. So So here's that trend just represented in another way. So we get increasing effective nuclear charge from bottom to top and from left to right. And so the top right-hand side is the highest values of effective nuclear charge. The highest of all on the periodic table is helium. All right, let's now talk about atom size. And so atom size, we can see from this little graphic down here, the largest atom is in the bottom left-hand side of the periodic table, and the smallest atom is in the top right-hand side. And this makes a lot of sense with our effective nuclear charge. So the outermost electron of cesium experiences a tiny effective nuclear charge, and so it strays pretty far from the nucleus. And the outermost electron of helium feels a huge effective nuclear charge and stays very close to its nucleus. So here we have now the actual values that these have been measured, and so you can see what I told you is true. Helium is the smallest and cesium is the largest. Okay, the size of an atom is determined by the outermost electron. As n increases, the radius increases, and so the effective nuclear charge does a good job of explaining the left to right trend. So the electrons are pulled closer to the nucleus as we go left to right, and then top to bottom is explained by the fact that we're increasing the principal quantum number. So this is n equals 1, this is a small orbital, n equals 2, n equals 3, n equals 4, n equals 5, n equals 6. So the principal quantum number increasing explains the up to down trend in size, and effective nuclear charge explains the left to right trend in size. Okay, now just showing the trends again, and we cut out the transition metals for a purpose because they're confusing. So the absolute largest atom here is cesium, which is in this bottom left-hand corner, and the absolute smallest atom out of these is helium, which is in this top right-hand corner. And as promised, these trends are directly opposite of each other. High effective nuclear charge means small atom. Low effective nuclear charge means larger atom. Just a different representation of that same trend. All right, we also need to talk about ions. So we've only been talking about atoms where the number of protons and number of electrons are the same. We should also talk about ions and what happens with those. So the first thing that we'll talk about here is removing an electron from an atom to make a cation. Okay, and in this case, the atom is always larger than the cation. Okay, there's no exceptions to this at all. Removing an electron from an atom makes a cation which is smaller. There's no exception to this other part too. So you take a neutral atom, which has the same number of protons and electrons, and you add an electron to make the anion. Okay, it's always the case that the anion is larger than the neutral atom. And we have one other trend that we need to talk about. It's in the case where we have an isoelectronic ion. Isoelectronic means they have exactly the same number of total electrons. If we go through this set, N3 minus, O2 minus, F minus, Na plus, and Mg2 plus all have exactly 10 electrons. Okay. In the instance, in this special case where what you were given is an isoelectronic set, the ion with the largest negative charge, so this is 3 minus, that's the most negative, is the largest ion, and the ion with the largest positive charge is the smallest ion. Okay? But only within an isoelectronic set can we make this type of analysis happen. Okay, so this is talking about that a little bit more. Same set again. Number of electrons that we have is 10 in each case, as promised. Number of protons increases across this set. Okay, it goes from 7 to 12. And that's why we get this tightening of the radius. So we have 10 electrons being attracted by 7 protons, and then 8, and then 9, and then here 11, and here 12. So this is a much higher charge, and also ends up being a much higher effective charge. And so this is the smallest, this magnesium 2 plus, this is the largest, the nitrogen 3 minus. Okay, so sometimes you'll be asked to rank a series of ions. if you were asked to rank these neutral atoms, you would say fluorine is the smallest and bromine is the largest. Well, it ends up, if we make a change of a set all by the same amount of charge, then the order is unaffected. And so fluoride is the smallest and bromide is the largest. Okay, they're all in the same column and all with the same charge. Another one that we'll run across sometime is, and that's analogous to what we were talking about up here, but not for isoelectronics, is if we have two atoms, this is the same metal, chromium 2 and chromium 3, the more highly positively charged the ion is, it will be smaller, and the one with the smaller charge will be larger. So chromium 2 plus is significantly larger than chromium 3 plus. Okay, just restating that again, the isoelectronic part. A special case where we have an isoelectronic set, the largest negative charge is on the largest ion, the largest positive charge is the smallest ion. All right, something that's also related to effective nuclear charge is this concept of ionization energy. The ionization energy is the amount of energy that it takes to take a gaseous element, so we've had to heat magnesium up really hot to turn it into a gas, and then we've applied a voltage to it to remove an electron. So how much energy do we have to put into this system to remove this first electron? Is its first ionization energy. And then we can continue to do this until we strip away all the electrons if we really wanted to. So I can take this magnesium plus 1 and strip off a second electron. And then I could continue to do that. The magnesium 2 plus I could strip off to make magnesium 3 plus and release another electron. And the only real thing that you guys should get out of this is we have a big jump here. So the first took about 700 to remove. The second took about double that, so not too bad. But then removing the third took a huge amount of energy. Right, it doubled, and if we were expecting something similar, I don't know, maybe this would triple, say, and we would expect 2100 for this. We had a huge difference here. And this is all related to the fact that the most stable cation for magnesium is magnesium 2 plus. And so it starts to be difficult to remove any more electrons past that. Here's a more detailed explanation of that. Removing a subsequent electron requires more energy. The third ionization removes an electron from an inner orbital, the 2p, and so requires a huge input of energy. Okay, so as you might expect, the highest effective nuclear charge is up here in this right-hand side, upper right-hand side of the periodic table. And so the highest first ionization energy is also up there. Okay, these electrons up here, these atoms are small. They have a high effective nuclear charge, so you got a small atom and the electrons that's tightly held. And so it's the most difficult to remove an electron from helium. It's the easiest to remove an electron from cesium. As the principal quantum number gets smaller, the electron is located closer and closer to the nucleus. That explains the up and down trend in ionization energy. All right, one final trend for us to talk about, electron affinity. Now we take an atom, we put it in the gas phase, and we introduce an extra electron to it. So we take an atom and we transform it into the anion. The greater the affinity an atom has for an electron, the lower the energy will be for the resulting ion. As a result, electron affinity values are always negative. Okay, so all of these are negative, but some are more negative and some are less negative. So fluorine, which actually ends up being having a very high electron affinity, fluorine takes an electron and releases 328 kilojoules per mole of energy. A mole of boron also will take an electron, but only releases 26.7 kilojoules per mole of energy. Okay, as the Z effective increases from left to right, the electrons are more tightly held, making it more difficult to ionize an atom, but easier to add an electron. As we go from left to right, it gets easier to add an electron, and harder to take one away. Okay, as the effective nuclear charge increases, the energy released from adding an additional electron also increases. As the quantum number gets larger, going top to bottom, the added electron is located closer to the nucleus and more strongly held. And then finally, because this would be good especially for a multiple choice question, you need to remember the noble gases have no electron affinity. This very last column over here, the electron affinity is 0. So what happens is we start on the left, the electron affinity is low, the electron affinity increases all the way over to the halides. They have the highest effective, the highest electron affinity. So for example, fluorine has a very high electron affinity. But then I go fluorine to neon and the electron affinity drops to 0. All right, well here's all of the trends together. And only one of them is the opposite of the others. So the largest atom is the bottom left-hand side of the periodic table. So the atomic radius increases from right to left and increases from top to bottom. All three of the other trends, effective nuclear charge, ionization energy, and electron affinity, increase from left to right and increase from bottom to top. And here's kind of to show you how all these electrons overlay each other. So for lithium, we have a 3+ charge in the nucleus, 2 electrons in the 1s, and 1 electron in the 2s. Beryllium, we add a proton to the nucleus and also add an electron to the 2s orbital. When I go from beryllium to boron, well, the 2s and the 1s and the 2s are full. And so the third electron goes into this 2p orbital, and then the next electron goes into a 2p, and we continue to do this so that all of these orbitals are overlaid with each other. And then finally, we also have the deal down here where, so if we start with the neutral atom oxygen, if I remove an electron, the cation is smaller than the oxygen atom, and then as I add electrons to oxygen, so O to make O minus, it gets bigger, and O minus to make O2 minus, it gets even bigger. So here the number of electrons increases, but the effective nuclear charge remains unchanged. Electrons push each other further away from the nucleus. And remember, finally, anions are larger than the neutral atom, cations are smaller than the neutral atom. And hopefully seeing all this together, you see how there's a correlation between these properties.